Before starting today's class, I'm going to make a correction. So in the last class, we discussed about the parallel circuit, right? So in this case, we have to calculate the probability of the union of T and B, right? So to calculate this equation should be transferred to 1 minus the probability of the complement of T intersection the complement of B, right? But in this case, if we want to change this equation to the multiplication of the probability of T prime and the probability of B prime, this should be independence, right? Okay? But in this case, the independence doesn't mean these two events have no intersection. Okay? Because the definition of the independence is that the previous event affects the next event. And that does not mean there is no intersection. So this cannot be derived based on the Venn diagram. But instead, we all know about this relationship. The probability of the union of A and B equals to the summation of the probability of A and the probability of B minus the probability of A prime intersection B prime, right? Probably you learned about this in your high school. So if we assume that the probability of A has A probability, and the A should be between 0, 1, okay? And if we assume that the probability of B equals to B, B should be between 0 and 1, right? Okay? So in this case, so from the example, so we should be change this sentence. Each device fails and operates independently should be changed to each device fails independently. 네, 이거죠? 그죠? So in this case, 그러니까 이 문장 틀렸어요. 이 문장이 책에 보시면 each device fails independently만 있어요. operate는 빠진다고 생각하세요. So that means each device fails independently. That is the definition from this problem. So from this equation, we can change this to A plus B minus A multiplied by B, right? Why? Because each device fails and each device is independent, okay? So if we provide 1 minus 1 here, and we can have A plus B minus AB, we can change this equation to 1 minus A multiplied by 1 minus B, right? Because this equation can be changed to 1 minus A minus B plus AB, okay? This is the same formulation with this one, okay? 그러니까 1을 더하기를 빼주면 요 나머지 식이 이렇게 바뀔 수가 있죠. 그죠? 이해되시죠? So in this case, this will be 1 minus, this is the complement of A, right? This is the A prime multiplied by B prime. Okay? So the probability of the union of A and B can be calculated by 1 minus the complement of A multiplied by the complement of B. That is equal to this relationship, right? Okay? So you can use this equation to solve this problem. Okay? So now we are going to study about the random variables. The definition of the random variable is a function that assigns a real number to each outcome in the sample space of a random experiment. And the particular notation is used to distinguish the random variable from the real number. So normally the random variable is denoted by an uppercase letter, such as large X here. And after the experiment is conducted, the measured value is denoted by a lowercase, such as small x. So large X indicate the random variable, and small x indicate the actual number of random variable, okay? So you can understand the definition of the large X, small x from the following explanation, following slide. So now we are going to learn about the continuous and discrete random variables. What is the discrete random variable? That is a random variable with a finite or countably infinite range. This means that we can count the number of random variables in the case of discrete random variable, okay? And there is also a continuous random variable. That is a random variable with an interval, either finite or infinite, of the number for each range. So in this case, we cannot count the number of random variable. Okay? 그러니까 discrete는 그러니까 무한정 가더라도 숫자를 하나씩 셀 수 있는 거예요. 그 안에 들어가 있는 개수를. 근데 continuous random variable은 infinite가 아니라도 이게 보통 뭐 크고 작다라는 부등호로 표현이 되기 때문에 숫자를 셀 수가 없어요. 그 사이에. 그거를 continuous random variable라고 합니다. 아시겠죠? So these are the examples of the discrete and continuous random variables. In the case of discrete random variables, these are the examples. First one is the number of scratches on a surface. We can easily detect the number of scratches on the surface, right? And there is also a proportion of defect part among 100 tested. In this case, we can count the number of defect part among 100 part, right? So we can have the proportion of the countable defective part among 100 tested. So this is a type of discrete random variable also. And there is also number of common stock traded per day, because we can count the number of common stock traded per day. So as you can see here, we can count the number of random variable in the case of discrete random variable. And there is also the continuous random variable. And in this case, electrical current and voltage, we can count the current and voltage, right? And also, the physical measurement, such as length, weight, time, temperature, and pressure, etc. Because if we precisely measure the weights, for example, weight, if we want to precisely measure the weight of some product, there will be, for example, 100.36254, blah, 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 right? So in this case, we cannot count the actual number of weight. So in this case, the physical measurements are included as a continuous random variable. So these are the brief explanation of the random variables. And from the following chapters, chapter 3 and chapter 4, we are going to discuss about the random variable minutely, okay? 그러니까 이거는 간단한 설명이고 이제 챕터 3하고 4에서 이제 랜덤 베리어블에 대해서 다루게 됩니다. 아시겠죠? So today, we are going to learn about the analysis of discrete random variable first. And this is the chapter 3. And this is the chapter outline. First, we're going to learn what is discrete random variable. Secondly, we are going to learn about the probability distribution, which is called 확률 분포 in Korean, and the probability mass function, which is called 확률 질량 함수. And then we are going to learn about the cumulative distribution functions, which is called 누적 분포 함수. And then we are going to learn about the mean and variance of a discrete random variable. Mean is called 평균 in Korean, and variance is called 분산 in Korean. And then we can learn about the discrete uniform distribution. And after that, we are going to learn about the binomial distribution, which is called 이항 분포 in Korean. And after that, we are going to learn about the geometric and negative binomial distributions. And we can learn about the hypergeometric distribution, which is called 초기 하 분포 in Korean. And finally, we're going to learn about the Poisson distribution, which is called 푸아송 분포. So these are the chapters which will be discussed in this chapter. Okay? And this is the learning objective for the chapter 3. And after careful study of this chapter, you should be able to do the followings. Firstly, you can determine the probabilities from probability mass function and the reverse. And secondly, you can determine the probability from cumulative distribution functions. And the cumulative distribution functions can be obtained from the probability mass functions and the reverse. And thirdly, we can determine what is the means and variances for the discrete random variables. And in this chapter, we can also learn about the standard deviation, which is called 표준 편차 in Korean. And firstly, we can learn about the selection of an appropriate discrete probability distribution to calculate probabilities in specific applications. And we can calculate the probabilities and calculate means and variances for each of the probability distributions presented. So these 5 things are the learning objective of the chapter 3. So first, we are going to learn about the discrete random variables. The many physical systems can be modeled by the same or similar random variables. And the distribution of the random variable observed in each of these common systems can be analyzed, and the result can be used in different applications and examples. And in this chapter, we present the analysis of several discrete random variables that frequently arise in applications. So, what is the discrete random variable? This is the first simple definition for the discrete random variable. And it is a random variable with a finite or countably infinite range, which means that we can count the number of random variables, okay? So, as I mentioned here, it is countable. For example, the random variable large x include the small x1, small x2, small x3, blah, blah, blah. So this is the actual number of the random variables, okay? So this is the first example. A voice communication system for a business contains 48 external lines. And at a particular time, when the system is observed, some of the lines are being used. That is the question. And let x denote the number of lines in use, okay? That is the random variable. then X can assume any of the integral values from 0 to 48. Integral value is called 정수 in Korean. So the system is observed at a random point in time, and if 10 lines are in use, the small x should be equal to 10. Okay? This is the actual number of the random variable. And this is another example. In a semiconductor manufacturing process, 2 wafers are sampled, and each wafer is classified as pass or fail. Assume that the probability that a wafer passes the test is 0.8, and the wafers are independent. The sample space for the experiment and associated probabilities are shown in this table. And these are the outcomes, right? And this is the probability. And these are the outcomes that we can obtain from this system. So, in this case, the wafers are independent. And if we denote that the pass is P and fail is F, okay? Okay? So in this case, there is a possibility that we can select the first wafer being classified as pass and second wafer being classified as pass, right? So this should be connected as end condition, right? The first wafer should be selected being classified as pass, and also the second part should be selected of the wafer being classified as pass. Okay? So the probability of this case should be equal to 0.8 multiplied by 0.8, right? Because the wafers are independent, and these are connected as end condition, okay? So this could be 0.64, okay? And there is also a possibility to obtain the first wafer being classified as fail, and the second wafer being classified as pass, right? So in this case, the probability of this case could be 1 minus 0.8 multiplied by 0.8, right? Since we have the probability that a wafer has 0.8, so should be 0.2, okay? So that equals to 0.16, okay? And there is also a possibility that we can select the wafer as and second wafer being classified as fail. So the probability of this case can be 0.8 multiplied by 0.2, that equals to 0.16. And there is also a probability that we can select both wafer being classified as fail, right? This is the last case. So the probability of FF should be 0.2 multiplied by 0.2, that equals to 0.04. Okay? So from this relationship, we can make this table. And X indicate the actual number of wafers being classified as pass. So this is 2, this should be 1, 1, and this should be 0, okay? So we can make this table from this relationship. So, as I explained in here, the probability that the first whopper passes and the second whopper fails defined as P multiplied by F, and the probability of PF can be 0.8 multiplied by 0.2, that equals to 0.16, okay? And the random variable X is defined as the number. So the last column here shows the values of X that are assigned to each outcome. So this is another example for the particles on whoppers. To define the random variable X to be the number of contamination particles on a whopper, the possible values of X are the integers 0 throughout a very large number, right? So this can be expressed as X should be 0. Because there is no minus contamination particle, minus number of contamination particle, right? So the small x, which is the real number of the random variable, should be larger than 0. But we can have infinite contamination particles, right? So this can be expressed as x should be larger than or equal to 0. So we can also describe the random variable y as the number of chips made from a whopper that failed to the final test. So the random variable y indicates the number of chips which fail the final test. So if there are 12 chips, then we can write the small y should be larger than or equal to 0, or n should be smaller than or equal to 12. Why? Because we don't know how many chips are failed to the final test yet, right? So we can express the real number of the chips that failed the final test using this expression, okay? But this should be the integral value, which is called 정수값. 0부터 12까지 어떤 정수값이 나와야 되긴 하겠죠. 하지만 지금 모르니까 이렇게 표현한다는 얘기입니다. So we are going to learn about the probability distributions also. And the probability distribution of a random variable x is a description of the probabilities associated with the possible values of x. A probability distribution of a discrete random variable can be a list of the possible values along with their probabilities. So normally we can express this as the table or figure. This can be explained in the later slide, okay? And also a formula that is used to calculate the probability in response to an input of the random variable's value. So this is the example for the probability distributions. There is a chance that a bit transmitted throughout a digital transmission channel is received in error. And let x equal the number of bits received in error in the next 4 bits transmitted. So in this case, the large x can be 0, 1, 2, 3, 4. And these are the small x. Why? Because there is a possibility that no bit received in error, right? That is x equals to 0, okay? And there is also a possibility that 1 bit received in error. So in this case, the number of bits received in error is 1, right? So x should be equal to 1, okay? So there is also a possibility that 4 bits received in error in the next 4 bits transmitted. So in this case, the actual number of the random variable x should be equal to 4. Okay? So we have 5 choices here. And the associated probability distribution of x can be shown in a table and also a graph. And this is the table, okay? And left axis indicates the possible cases. For example, the probability of x is equal to 0 indicates received in error, okay? And also, x, the probability of x, which is equal to 3, indicate the case that there are 3 bits received in error. So these are the possible outcomes, okay? And the right column indicates the probability for each case. So the probability of x, which is equal to 0, is 0.6561. And the probability of x, which is equal to 2, is the 0.0486. Okay? So the summation of all these probabilities should be equal to 1. And also, this can be expressed by using the graph. The x-axis, which is expressed as small x, the small x is the real number of the random variable, right? So that can be 0, 1, 2, 3, 4, right? So for each case, we can have the probability. And the probability of the case when x equals to 0 is 0.6561. That is similar, that is identical to this case. And also, there is a probability of 0.0001 when x is equal to 4. This is also identical to this one. So you can choose either using the table or the graph. Now, we are going to learn about the probability mass function. The probability mass function is given by this example, this equation. The probability mass function can be expressed by the small f, x, okay? This is the equation representing the probability mass function, okay? The probability mass function can be divided into 2 parts. First one is the probability of x when x is equal to small xi. And in this case, the x equal to xi and I can be 1, 2, 3, 4. And for other cases, the probability mass function should be equal to 0. And this can be understood by the following example. Okay? 그러니까 어떤 구간에만 딱 정해서 그 구간의 총 probability가 1이라고 가정하면 그걸 벗어나는 곳의 확률을 제로라고 보는 거예요. 이거를 probability mass function이라고 생각하시면 됩니다. 아시겠죠? So, this is also probability mass function, right? Why? Because we are only consider about the bits received in error in the next 4 bits transmitted. And for other cases, the probability should be 0. Okay? Because the summation of the total probability is 1 here. 아시겠죠? 그러니까 이 경우도 그러니까 4개의 빛만 지금 그러니까 4개의 빛이 있을 때 그게 에러가 날 확률에 대해서만 고려하고 있는 거잖아요. 그러니까 다른 케이스에 대한 확률은 0이라고 놔야지 요거에 다 더한 확률이 1이 되겠죠. 그러니까 어떤 구간에 대해서만 그 구간에 대해서 확률을 평가하고 싶을 때 probability mass function 쓰시면 됩니다. 아시겠죠? So, for a discrete random variable x with possible values x1, x2, blah 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 xn, a probability mass function should be larger than 0 or equal to 0. And also, the summation of the probability mass function from I equal to 1 to n should be 1. Okay? 당연히 다 더한 값이 1이 돼야 된다고 아까 그랬죠. So this is the definition of the probability mass function. Okay? So this is the example regarding the probability mass function. Let the random variable x denote the number of whoppers that need to be analyzed to detect a large particle of contamination. And assume that the probability that a whopper contains a large particle is 0.01. And the whopper are independent here. And determine the probability distribution of x. That is the question. P denotes the whopper in which a large particle is present. And A denotes a whopper in which a large particle is absent. The sample space is infinite. Why? Because there is a possibility that we can select the whopper with contamination at the first time, right? And also, there is a possibility that we can select a whopper without contamination at the first time, and we can select the whopper with contamination at the second time, right? So that is PA, okay? Oh, AP, okay. Sorry. That is the possibility that the whopper without contamination, right? And there is a possibility that we can select the whopper with contamination, okay? And also, there is a possibility that we can select the first and second whopper without contamination, A. And also, we can select the third whopper with contamination. That is P. So this can be repeated infinitely. So the sample space is infinite. But as you can see, this is countable. So this will be the discrete random variable. Okay? 그러니까 이게 무한정 가더라도 지금 하나씩 다 셀 수가 있잖아요. 그럼 이거는 discrete random variable로 들어갑니다. 아시겠죠? So in this case, consider of the case x equals to 1. So the probability of x equals to 1, that should be, we have to select the first whopper with contamination, right? Because this is the number to select the whopper with contamination. So that is 0.01, okay? Because from the question, the probability that a whopper contains a large particle is 0.01, okay? And also, using the independence assumption, what is the x equals to 2? There will be the probability of x equals to 2. In that case, we have to select the first whopper without contamination, right? And we have to select the second whopper with contamination, right? So what is the probability that we can select the first whopper without contamination? That is 0.99, okay? And multiplied by 0.01. Why? Because the question say, please use the independence assumption. So this will be 0.0099. So from these two cases, we can simply understand that the probability that we can select the first whopper with contamination has a higher possibility to select the first whopper without contamination and second whopper with contamination. Okay? And from these two cases, we can make a general formulation for this example. That is, the probability of large X equals to small x. Okay? And that can be the probability of A, blah, 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 A, and P. A indicate the case that the first whopper contains no particle, and P indicate the case that the second the whopper includes the contamination. Okay? So this can be the x minus 1's power of 0.99 multiplied by 0.01. Okay? So that is the general formulation for this question. So now we are going to learn about the cumulative distribution functions. The cumulative distribution function is based on the probability mass function. And the cumulative distribution function of a discrete random variable x is denoted as large F and x. That can be expressed by this equation. cumulative가 한국어로 누적이라는 뜻이죠, 누적. 그죠? 누적되니까 서메이션이 당연히 들어간다고 생각할 수가 있어요, 그죠? So, the cumulative distribution function fx should be equal to the probability of x when the x is smaller than or equal to the small x, okay? And that can be the summation of x I smaller than or equal to x, the probability mass function of xi. Okay? That is the definition of the cumulative distribution function. So, from this equation, we can calculate the cumulative distribution function from the probability mass function here. Okay? 그러니까 probability mass function의 summation이 cumulative distribution function이라고 생각하시면 돼요. 아시겠죠? So, for a discrete random variable large x, fx satisfies the following three properties. First one is this equation, and second one is that the cumulative distribution function should be between 0 and 1. Okay? And also, if the small x is smaller than or equal to y, then the cumulative distribution function of x also should be smaller than or equal to the cumulative distribution function of y. These are the three properties for the cumulative distribution function, okay? So this is another example. So in the previous example, 3-4, we might be interested in the probability of 3 or fewer bits being in error, and can be denoted as the probability of x which is smaller than or equal to 3, right? 지금 요거는 3개나 또는 그보다 작은 빛을, 그러니까 에러를 갖는 빛을 포함하라는 얘기니까 이렇게 표현이 되죠, 부등호로. So these are the table. And x in the number of bits being in error, okay? And this axis indicates the probability for each case. And this is the cumulative distribution function, right? So the event that x is smaller than or equal to 3 is the union of the mutually exclusive events, such as the event x is equal to 0 and x is equal to 1 and x is equal to 2 and x is equal to 3. So in this case, the previous case, for example, when the x is equal to 1, this does not affect to the case that the x is equal to 2, right? So these are the mutually exclusive, okay? Because they don't influence each other. So in this case, from the table, we can calculate the probability of x when the x is smaller than or equal to 3. How? That can be the summation of the probability of x when x equal to 0 plus the probability of x equals to 1 plus the probability of x equals to 2 plus the probability of x equal to 3, right? Because for this expression, we can have all these 4 things, right? There is a possibility. So this can be 0.6561 plus 0.2916 plus 0.0486 plus 0.0036, and that will be 0.9999, okay? And also, what is the probability of x when x is equal to 3? And we can easily obtain this value from this table, right? This is the answer. But we can also calculate this by using this equation. The probability of x when x equals to 3 should be equal to the probability of x which is smaller than or equal to 3 minus the probability of x which is smaller than or equal to 2, right? So from this relationship, we know about the probability of x when x is smaller than 3 or equal to 3. That is 0.9999, right? And also, if you calculate this from this equation, we can obtain the value 0.9963. This will be 0.0036. So we can simply calculate the probability of x when x is equal to 3 from this table or from this equation, okay? And this is another example. And to determine the probability mass function of x from the cumulative distribution function, this is the expression for the cumulative distribution function, okay? So now we are going to express this based on the graph, okay? The x-axis indicates the small x, and the y-axis indicate the cumulative distribution function, okay? So in this case, the cumulative distribution function is divided into 4 sections. That is -2, 0, and 2, okay? So in this case, when the small x is smaller than -2, there will be this part, right? And the case that the x is larger than or equal to -2 and smaller than 0, there will be this part, okay? That is 0.2, okay? And when the x is larger than or equal to 0 and smaller than 2, that is here, right? And also, when the x is larger than or equal to 2, the cumulative mass function should be 1. Okay? So in this case, how can we calculate the probability mass functions of -2, 0, and 2? So we are going to think about this part, okay? The probability of mass function xi should be equal to 0 when the xi smaller than -2, right? Otherwise, the cumulative mass function should not be 0. Okay? Okay? 그러니까 만약에 이게 probability mass function이 값이 있으면 cumulative mass function이 제로가 될 수 없겠죠. What about this case? The probability of mass function xj should be 0 also when the xj larger than -2 and smaller than 0. Why? Because in this range, the cumulative mass function is not changed. So, from these two relationships, we can determine that the probability mass function of -2 should be 0.2. Okay? And we can think about this part also. If we assume that the probability mass function of xk should be 0 when xk is larger than 0 and smaller than 2. Because otherwise, the cumulative mass function in this range should be changed. Okay? So, the probability mass function of 0 should be 0.7 minus 0.2. Okay? That is 0.5. Okay? And also, we can apply the same procedure to here. If the probability mass function of L should be 0 when XL is larger than 2. So in this case, the probability mass function of 2 equals to 1 minus 0.7, that is 0.3. Okay? So we can calculate the probability mass function, in this case, from the cumulative distribution function. And this is another example for the case of sampling without replacement, okay? And a day's production of 850 parts contains 50 defective parts. So in this case, 2 parts are selected randomly, which means that equally likely without replacement, okay? So let the random variable x equal the number of the defective part. So what is the cumulative distribution functions for this question? So in this case, we have three options. That is large F, 0, large F, 1, large F, 2. Okay? So we have to calculate all these three things to calculate the total cumulative distribution function. So this can be rewritten as the probability large X should be smaller than or equal to 0. Okay? And this also can be the probability of should be smaller than or equal to 1. And this can be the probability of X to be smaller than or equal to 2. Okay? So in this case, this should be the probability of X which is equal to 0. Right? Because there is no minus case in this here, right? Because X is the number of defective part. There is no minus number of defective part. 그러니까 defective part가 마이너스 1개일 수가 있어요. 그러니까 없거나 1 이상이겠죠? 그러니까 0보다 작거나 같다는 것은 0이다라고 표현할 수가 있겠죠. So this can be, what is the probability of this case? That is, both of the two parts should be non-defective. Okay? So the first part should be non-defective. That is 800. Okay? Multiplied by, this is connected as AND condition, right? Because the X should be equal to 0. That means there is no part, there is no defective part. That means we can only select the non-defective part. So the first part should be non-defective, and the second part should be non-defective also. So they should be connected as AND condition, which means that this should be connected as multiplication rule. So the second one can be 799 divided by 849. Okay? Because this is the without replacement. We already select the first part, non-defective part. So there are 799 non-defective part left among 849 part. Okay? That is 8. Okay? And what about this case? This can be the summation of the probability of X, which is equal to 0, plus the probability of X, which is equal to 1. Right? So in this case, we already calculated this value. Right? So we need to calculate this parameter here. And the probability of X, which is equal to 1, can be, this is the case that only one part is defective. So there are two options that we can select first non-defective part, and we can select the second defective part. And also, we can select first defective part and second non-defective part. Right? So this can be 800 divided by 850 multiplied by 50 divided by 849. Okay? Plus, because there are two options that is connected as OR condition. This or this, right? So that is 50 divided by 850 multiplied by and that is 0.111. So this summation can be 0.886, 0.111, that is 0.997. And also, we can calculate this. This can be the summation of x equals to 0 plus the probability of x equals to 1 plus the probability of x equals to 2, right? So we all know about the first and second part here, okay? Because we already calculated from these two equations. So we have to obtain this value. And in this case, we have obtained all of the two being as defective part, right? So this can be 50 divided by 850 multiplied by 49 divided by 849. Okay? So that is 0.003. Okay? So this cumulative distribution function can be 0.886 plus 0.111 plus 0.003 equals to 1. Okay? And this is the numbers of probability distribution. The mean is a measure of the center or middle of the probability distribution. The mean is called 평균 in Korean. And there is a variation, which is a measure of the dispersion or variability of the probability distribution. So this can be used to determine the scatterness of the probability distribution, okay? Which is called 분산 in Korean. And there is also standard deviation. And this is another measure of the dispersion, which is the square root of the variation, okay? Which is called 표준 편차 in Korean. So now we're going to learn about all these three things. First one is the definition of mean. The mean or expected value of the discrete random value of x, denoted as mu here, or large E, large X. And this can be expressed by this equation. The average equals to the summation of x multiplied by the probability mass function. Okay? So there can be x1 multiplied by the probability of x when x is equal to x1 plus x2 multiplied by the probability of x when x is equal to x2, blah, 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 okay? So this is the definition of the mean for the discrete random variable. So the mean represents the center of the distribution. And if fx is the probability mass function representing the loading on a long or thin beam, Ex indicates the point of balance for the beam. This can be explained in the later slide, okay? And this is the definition of the variation. The variation of the discrete random variable x denoted as sigma square or large V, large x. So this is the equation for the variance. The sigma square equal to the summation of x minus mu. Mu is the mean, right? Square multiplied by the probability mass function. Okay? That is the definition of the variance. And I'm going to derive how to change this equation to this. This is the definition of the variation, right? Variance. And this can be sigma x, x square minus 2x mu plus mu square multiplied by the probability mass function. Okay? Okay? And this also can be the sigma x, x square, the probability mass function minus 2 mu sigma x, x multiplied by the probability mass function plus mu square, the summation of the probability mass function. Okay? So what is this? Mean. Yeah. This is the mean, right? What is the summation of the probability mass function? This one, right? So this can be x. The summation of x square fx minus 2 mu square, right? Plus mu square. Okay? And this can be the summation of x square fx minus mu square. Okay? So from this relationship, we can simply calculate the variance of the discrete random variable using this equation. Okay? Understand? So the variance is the measure of dispersion or scatterness in the possible values for x. And this exhibits the average and distribution. And this point indicates the mean, okay? And the scatterness of this point indicates the variance, okay? So if we assume that this is the beam, and this is the point load, if we resist this beam at the mean point here, this beam can be balanced, okay? That is the definition of the mean. And even though these two cases have the same mean, the scatterness is different, right? So the A case indicates much higher variance as compared to the case of B. 그러니까 평균이 같다고 하더라도 이 데이터 포인트의 넓이, 그러니까 편차는 같을 수는 없죠. 그러니까 같을 경우도 있지만 안 같을 경우도 있죠. 그죠? 그래서 그거를 의미합니다. And this is about the different distributions, but the same measures. Figure 3 shows the two probability distributions that can be differed, although they have identical means and variances. And if we assume that the y-axis indicates the probability mass function, this is the each probability mass function, right? So in this case, we have the same mean, same variance, right? But even though we have the same mean and same variance, the shape of the probability distribution function is different, okay? So it is impossible to determine the shape of the probability distribution based on the mean and the variance, okay? And this is the example. And in the previous example 3-4, there is a chance that a bit transmitted throughout a digital transmission channel is received in error. And x is the number of bits received in error, the next 4 transmitted. So what are the mean and variance in this case? So x can be 0, 1, 2, 3, 4, right? So this is the table, okay? And the average or mean can be the summation of x multiplied by fx, okay? That is the definition of the mean, right? So this can be 0 multiplied by f0 plus 1 multiplied by f1 plus 2 multiplied by f2 plus 3 multiplied by f3 plus 4 multiplied by f4. Okay? So this can be 0 multiplied by 1 plus 1 6 plus 2 right? So in this case, the answer will be okay? That is the mean for this case. 그러니까 평균적으로 0.4 빛이 에러가 된다는 것이에요. 그죠? 왜냐면 x가 제로일 경우가 에러가 없는 경우의 확률이 가장 크죠. 그죠? 그러니까 평균이 1이 안 되고 0.4가 된다는 얘기입니다. 아시겠죠? So what is the variance? The variance is sigma square, and it can be the summation of x square fx minus mu square. Okay? And this can be 0 square multiplied by 0.6561 plus 1 square multiplied by 0.2916 plus 2 square multiplied by 0.0 plus 3 square multiplied by 0.0036 plus 4 square multiplied by 0.0001 minus 0.4 square. Okay? That is 0.36.